In this video, I will be taking a tensile specimen and holding it at one end and displacing the other end by a certain amount very rapidly, okay? And would like to see how the specimen performs and also display the damage when and if it fractures. Keep in mind that I'm not I'm not assessing the validity of such models or the accuracy of it. But what I usually do in this play series is take problems that are done entirely using the Abacus CAE program in a different by a different user and retrace the steps in the 3D Experience native FEA solver, which happens to be Abacus. So these tutorials are mainly useful for people who are either entirely new to 3D experience or they're thinking about migrating from Abacus CAE into the 3D experience platform. Now, the problem that I'm doing is shown here dimension-wise. This is a two-dimensional sample, and it's not drawn to scale, by the way. And what I do is I take the bottom of this and hold it or clamp it, and the top piece, all the points on the top of this line are moved by 20 millimeter. This particular problem is done in its entirety by the link shown below in the Abacus CAE, and you can see the correspondence between the interface and dialog boxes and things like that if you go to this particular reference. Now, there are some differences. For example, and I'll mention as I go along. For example, in this reference, the displacement is 5 millimeter, but when I did that, I did not get any damage in the which causes basically separation of the two pieces with 5 millimeter. Okay, that's one. The material properties are given here, and I am using uh, linear Breck elements to do that with reduced integration. Uh, that reference uses actually the full integration. Now, the other thing is that the plasticity data is over here. This is the same thing that I took from the reference. And there is the damage data that's given on the right side. And once again, this displacement failure uh, in that reference is initially indicated to be 0.5 millimeter, but when it comes to Abacus input, he puts down 0.065 millimeters, so that's exactly what I'm going to be doing. Okay. Now these are all fictitious numbers, so they don't necessarily mean that uh, can be used for your own problem, whatever it happens to be. The total duration of uh, the pull is a millisecond, 0.01, 0.001, and I will, because it's a dynamic problem in explicit formulation, you need to specify the amplitude, how fast uh, this is being applied. So that 5 millimeter uh, 5 millimeter displacement translation, oh sorry, 20 milliliter this translation is over a very short period of time. Now uh, this is not the scale. This is not does not have units here. So so what I'm saying here is that uh, 0.001 of 1 millisecond is what it takes for the displacement to take place. That's a huge dynamic problem. Okay, we're going to come back to I have some other slides, but I'm going to come back to them later on. I'll come to these later on. Okay. All right. So let's go ahead here and we make the part. The different ways of doing it. Here is the way I'm going to go about doing it. So I'll make a rectangle here, a centered rectangle of size 200 millimeter uh, lengthwise and 20 millimeter wide. So let's put some dimensions there. So this is going to be 20 millimeters, 20. and this height is going to be 200 based on that drawing that I showed you. Okay, so this is pretty much almost my sample. Now I'm going to draw my the cutout piece. So there are different ways of doing it. Here's how I'm going to do that. So I'll use a 3-point arc. So for example, let me zoom in for a second. So let's try it. 1 point, there. Okay. Now we do have to clean it up here. For example, this point, the dimension from here to the up there should be what is that? 30 millimeters. So the dimension from this point to that point should be 30. And same thing down here. So the dimension from there to there should also be 30. And the radius, this radius must be 492.5. 492.5. All right. And now we're going to do a bit of a cleanup there. So using quick trim, I'm going to get rid of this line there. And the other side is just mirror. We can just mirror it. So we go here to the mirror, mirror that arc with respect to this line, and quick trim this other piece, vertical line. Oops. Okay, good. That's fine. So exit, and we're going to pad this thing by the thickness of the sample is 5 millimeters. So we're going to pad this thing by 5 millimeters. All right, so the sample has been constructed. Now, I would like to, because if you look at the drawing, there is a line here. I need to make a partition of this. But the partitioning in Abacus is different from partitioning, or at least the way it's done, it's not the same, exactly the same step. But I do need two planes which are you're going to be used for partitioning purposes. So for example, I'm going to make a plane from that top plane, but in the other direction, and 30 millimeters to bring it down to that line, basically. See, this is going to be one of the planes. Okay, notice that they're lined up, and then another one on the other side. Let me do another one, another plane here. So from this plane in the other direction, a 30 millimeter. So these are the two planes that are going to be needed later on to make the partition. Okay, let's do a quick save, and we're going to go and create our material. Material under tools, here is a material browser, but we're going to make one, create a material. I'm going to give it a name, so I'll say tensile sample, and then October 23rd, 2023. This is so that I can find them easier if I ever have to. Now, that name is going to be created in the database. Of course, we have to put in the data. Okay, so right there, tensile test, October, actually, what I want is not this, I want the 23rd, right, tensile. Let me close that and browse it again, because it takes some time for it to appear, and it's right there. Tensile sample, October 23rd, this is the one that I made, okay? So I'm gonna apply, I'm going to apply it to that part, and you say green check mark and close that. You don't need it. Now you can go and plug in your values. So we go here, double click. All right. Because this is a dynamic problem, I need the density. So here's the density and 7,800 so steel, 7,800 kilogram per meter cube. Let's go and put in the Young's modulus, etc. So Abacus multiphysics, mechanical, elasticity, elastic, and the Young's modulus is 200 GPa or uh, 200,000 megapascal right there. Poisson ratio, I was told that it is, let me see, 0.3. Poisson ratio is 0.3. Okay. Then we're going to go and do plasticity, metal plasticity, plastic, and we put our values. So there was, if you look at this graph, you can put in our numbers, 300, 0, that's the yield strength. And then there is 400, point, 0.001, and then 600, and that is 0.003. Okay, so that takes care of plasticity. Then we go to damage, ductile damage. Okay. Now here, because the strain rate is also specified, I need a third column. So let's go ahead and add, say, use strain rate dependent data. Now we have the third column. We put in exactly those numbers that I had, namely 0.1, triaxiality 0, and this is 1. So these numbers that you see here are actually these three numbers. Okay. Then I have to initiate the damage evolution, and I'll come back and talk about this thing later on. Okay, we'll talk about this thing later on. Let's go ahead here. What if you don't do that? So if you look at under ductile damage, there's an option here, damage evolution, and this number, displacement, see displacement, displacement at failure 0.065, which I mentioned that the user, that YouTuber initially in the description of his problem puts down 0.5, but when it comes to Abacus input, just uses 0.065, and I'm going to use the same thing. Now, notice that these white sheets are there. That means they're both specified. If I use this X, that will go away. Okay, so I'm not specifying damage of it, but I do want both of them to be specified. So we say okay. That's pretty much it as far as this is concerned. Now we're going to go and create our mesh. There are two ways of doing it. You can, for example, say right click, put it on the very top. Right click, insert finite element model. That will take us to the structural model creation where I can do the meshing. That's one way of doing it. The other one is just switch workbench, switch application, and go directly yourself to the structural model creation. Even if you did the first way, it'll take you to the same spot. Okay, so MTFEM. Good. No, in both cases, you go to structural model creation. Now, when you go there, you can go mesh it, but these partitions are not made, so it does mesh whatever it wants, the way it wants to. So, in order to partition this thing, as I said, this is very common in the Abacus CAE partitioning. So you go to Setup, Standard. You go to Standard tab. This is the uh, uh, action bar for. We call it action bar for 3D experience. It is a standard tab, and expand this icon, this pull down menu or pull up menu called model prep. This is where you can actually partition things. Okay, so standard model prep, it'll put you in the model prep in a minute. And then it says, okay, what is the thing that you want to partition? Is it a shape? Or do you want to fool around with? Is it the shape or is it a copy of the shape? No, I'll do the shape. That's okay. But otherwise, you do the abstract. So we say, okay. And when you do that, it will put you in the simulation model prep. You can see that right up there. And the icons, notice the action bar change, the icons. There is an idealized tab. If you select the idealized tab right there, partition. Okay. So you click, it says, okay, what is the volume to partition? What is this whole thing? What is the cutting element? It is this, okay? And then we say, okay. Notice that it did create, if I hide this, you can see that. If I hide that plane, you can see that it essentially cut it, okay? The problem with the splitting directly is that it says either select the top or the bottom. But when you partition, it keeps you both. So do it again. This piece, partition it with that plane, and there we are. If I hide this, you can see that it actually partitioned. These other planes, if it's bothering you, I can hide them. Hide. Okay. Now we have to exit this because this is an application, simulation model prep. I don't want to be there. I get out, back to my mesh. Okay. So here is the mesh tab. And this is a partition object, and I'm going to make a partition hex mesh. Partition hex mesh. See that? Partition hex mesh. There are other ways of doing it. There are other things you can do, but if you have a partition part, and it's very, this is very useful for it. You click on it. All right. The support is obviously this whole thing. When it turns green, it means that it actually can be result in a structured mesh, okay, just to let you know. And let me see now. I said the size is going to be a global size of 1 millimeter. So 1 millimeter is already fine. And then we say mesh. And if you look close enough, it's exactly what you want. Okay? So we say okay, right there. You can see. Excellent. Now, a couple of things I want to do, and that is, first of all, we have to apply the properties of this, because notice that it did create a mesh for us, but there's no properties. It doesn't know what material. So we can go to the properties, we select the solid section, and then you can either do it by the part or by the mesh. Doesn't matter. I'll use the whole part. Notice that the proper material was selected, tensile sample, and then we say OK. Now, there's one other thing I want to do, which may not be well. Let me tell you what the idea is. I want to create a group of nodes up here, or a set of nodes that eventually are going to be pulled up, and a set of node down here, which are going to be which are going to be held in place. Now, Abacus calls it set, but there is no such a thing as set here. So let me go ahead. It's called groups. Okay, so let me create a group. So there are these uh, yeah. So let me create groups, and there are different ways of doing it. I'm going to create a group, and I'm going to create it by the spatial group. Spatial group means that you make a box or a sphere. Anything, any node or element within that sphere is going to go into that group or in that box. So first thing I'm going to do is I'm going to look at the view from the front, so that it's easier to, sorry, view from the front, which is easier for me to make that box for you. So front view is right here. All right. So we go to group, and it's going to be a spatial group, and you can make a box or you can make a sphere. Obviously, a box is nodes is what I want to take. I don't want to take element. I want to take the nodes, and I'm going to say okay. So let's go make it. Let me call this thing, by the way, bottom. Let me call it bottom spatial group. So I make a sphere here, not a sphere, a box, which includes all these elements uh, that I want in it. Now click, turn around, you see, it picks all those nodes, and then I have resized the box. You can resize the box so that you pick all the nodes be inside of that box, which is exactly what I want. You say okay, and if you want to know, by the way, how many nodes are there, double click on it, update. It says there is 3,000 nodes in it. Okay, so that's fine. So these are all the nodes that I want. Now I want to create another one, which is called the top one. Do exactly the same thing for that top. There are other ways of doing this thing, by the way. To view, front view. Okay, let's go make another one, another group, a group, another spatial group. So make a box so that it has all the nodes above that basically line. You click, you turn around, if necessary, resize. And I do have a resize here. Yeah, everything is in there. And I call this thing top TOP. TOP. Okay, good. I bet it's gonna have the same number of nodes. Let's do a quick save here. All right, so we are done. We're done there. Uh, now we're gonna go to the mechanical scenario or mechanical scenario creation. The finite element can be done either there or there. These are both Abacus. This one, if you want the Abacus explicit, the license is here, not there. Okay, so I click on mechanical scenario creation. It's a structural analysis that I want to do, and the model is the one that I created. Notice that here it says model 17111, model 17111, finite element model. We say okay. Okay, good, good. So here is our case basically right here, which is I think it's the analog of a job, if I'm not mistaken. But anyway, let's go ahead and do that. Uh, so we go to procedure, and we want to do explicit dynamic procedure. Notice that this says no procedure, right? So you have to go there, explicit dynamic. This message pops up, but I don't agree with it because it will work. I mean, it says that these global elements, the element use are not, cannot be used in explicit dynamics. I don't believe that is correct. So in fact, we'll see. The total step is 0.001. Okay, everything else is all right. Good. And now we're going to apply our stuff. So, well, first of all, I don't want to see this whole thing. Right click visibility manager. I don't want to see my elements, so let me uncheck them because it's too fine, you can't see much. All right, so as far as the boundary condition is concerned, I'm going to clamp the stuff at the bottom, okay? So there's two ways to do it. You either go, sorry, boundary condition. This thing is pinned. I don't want it to be pinned. That's why I could not select this. What else is pinned? Okay, so we go boundary conditions. Okay, we go here. Okay, we go here to clamp, fix either clamp or fix displacement. Oh, okay, I'll use a clamp, and I can do it by sets, by groups, basically. So right click by groups, finite element group, and I created them. This is the bottom one. Okay, notice that they're all clamped right there. All right. Now the top one, I want to let it move in the vertical direction. So what I'm going to do is, instead of using clamp, I'm going to use fixed displacement, and again by groups, and it's the top group. And I want to say that it can move in the direction, it cannot move in X and Y, but it can move in Z, okay? and we say fine. All right. Uh, is it there? Let's check it out. It's fixed displacement. Yeah, it's this one, right? It's that one. Yeah. But I do want to give it a translation, upward translation. Now, when it comes to giving a displacement, let me show you, for example, when you say under translation, apply translation, you need an amplitude here. So why don't I go and make my amplitude? Because even though I may fill this thing and say 20 millimeter in the vertical direction, it's going to come back and say you need an amplitude. So let me say cancel that. Where do we make amplitude? Let's go to setup, uh, tabular amplitude. You click on it. So here's what I want. When it's 0, this is 0. When this is 0.001, total height is 1. Okay, in terms of amplitude, and that is this plot, this thing, right? Okay, so we say okay. So I created something called amplitude. I'll call this thing my amplitude. My amplitude. All right, good. So let's go ahead and now to boundary conditions. Apply translation. Group is going to be the top group. By group, let's do it by groups. Is the top group. Yeah. So translation of 20 millimeter in the direction Z. In the direction Z. Say okay. Oh, I forgot the amplitude. That's why this didn't turn updated basically. So not the default, but my amplitude. And then we say okay. Notice that this is not complaining anymore. Uh, you can see the let me show you. Let me say show me the mesh too. Okay, so hang in there because you might say where are the icons there? Where were the icons for translation? So let me see. What's the best way of doing this thing? Okay, so we have applied our clamp. We have applied our fixed displacement. This is a fixed displacement on the top spatial group. You can see that, and there is the translation up there with 20 millimeter upward with that amplitude. All right, that's pretty good. Let's go ahead and save it and then run it. Oh, element type, element type. Let me go and change the element type. If you go if you go here, right here in the tree, there is this branch which says element type assignment. Okay, and if you double click on it, it says the reduced integration. Okay, what I mentioned, the reference, YouTube reference that I'm using, did not use the reduced integration. They used the C3D8, which is fine. We're going to just leave it the way it is. Okay, good. Let's go ahead and run it. First thing we're going to do, simulate. Let's do a model check. If there are any obvious errors, obvious things that we forgot, they're going to turn out here. It looks fine so far. Okay, good. Then simulation check incidentally, you see something there, that's because of those restraints that we put in there. Remember I said that don't move in the y and z, x and z, x and y, but moves in z. So that's what this thing is. Simulation check. Any obvious things in a different category of stuff is going to pop up there. All right. I don't anticipate any issues, maybe some warnings, but that's about it. And then once this finishes, then we're going to simulate, which means essentially submit or run. What we're doing here is equivalent to data check in Abacus CAE, if you're familiar with. Otherwise, it's just checking. Okay, good. And then we're going to run and simulate. And this is going to be very fast. It hasn't started yet. Once you get the dialog box and you say okay, then it's going to start actually running. Okay, now we say okay, and this is where the run starts. Let me click on the iterations here. This is like the monitor thing that you do in Abacus, the Abacus program, Abacus CE program. Here is the wall clock, which is the total time in real seconds. This is the this is the true time in seconds, 15 seconds, 16 seconds, etc. And these are time steps and things like that. 39% complete, 44. It's almost done. Extracting results. Close that. Let's do a simulation. I'm going to do a plastic strain. Okay, slow it down. I'm going to exit this. Let's go. There's something wrong here, definitely. Plastic strain is this. Okay, it's definitely something wrong. So let's find out what the issue is. Plastic strain, displacement. I must have made a mistake in. Oh, meters! Whoa! Whoa! Applied translations, not 20 meters, 20 millimeters. Run it. Just be aware of the fact that there's a lot of garbage in, garbage out. Could be. Here's the iterations. That's one danger with the explicit dynamics is that because there is no equilibrium check involved, there's no convergence, and basically things can go through, give you numbers and colors, but whether it makes sense or not is a different story. Even these damaged models, you can put random numbers there and it will work. I mean, that remember, the purpose of these tutorials is not to actually assess the validity of those damaged model or damaged parameters that you put in. It's just show you if this was done in Abacus CAE, how do things translate when you are to do it in step-by-step fashion in 3D Experience. That's what the purpose of these particular playlists are. Almost done. Okay. Okay. So let me close that. There we are. So animate. This is the displacement. Now let me switch this thing to plastic strain. And here we can slow it down if needed a little bit. But anyway, I'm going to stop this, exit that. This is where things change. Now, I told you I was going to go back to these slides. There's two more slides that are left. I want to go back to them. And that is not this. Okay. Remember, I had this situation. These two, when I created the material properties, these two white sheets of metal were there, which means that I have specified both of them, ductile damage and damage evolution. And I put down 0.065. Now, what if I just use the red check mark here to remove the damage evolution? What if I do that? So here, look, there's no white sheet here. That means I put my cursor there, click on it, and it removed it. Now, when you run it, you don't see any elements damaging in the sense that basically leads to the fracture of that. And here's the, we will give you after 1 millisecond, these are the plastic strain, no break here. Now, what if I went back there and put this thing in, but put some dummy number there? For example, nothing at all. Here, 0. You run it. It works. I mean, it shows you fracture. So if you want to see these things failing, this must be checked. Now, what you put in there is irrelevant. Now, when you say irrelevant, I mean, these numbers obviously are important. So, as I said, we're not assessing the validity of these numbers, random numbers that we put in there, which I took from that reference, by the way. Now, if you compare this, see that? If you compare this with the stuff on the previous page, okay, let me go to the previous page. The numbers are not the same. So, oops, sorry, let me see, hang in there. Yeah, right here. The numbers are not the same. One had, zero point 0.1, the other one was 0.147. But right there, for the value that the YouTuber used, 0.065, I got those contours that I just showed you. But now I get this, so it breaks, but looks like that. Now, the other thing is that in I don't have to in some of these Abacus CAEs that CAE tutorials that you look at, they go to the status and check this thing. I did not check it, so it still work. Whatever they have done is they fix that in the 3D experience run. Okay. But in the Abacus CAE, it looks like if you don't check this, you're not going to see elements failing unless they plan to change that later on. Okay, so that's pretty much it. Okay, good luck.